What if I told you that the surfaces of a donut and a coffee mug are extremely similar? You'll look at me funny, but they're actually so alike they can be thought of as the same. Not convinced? Well, think about it this way. Imagine you have a donut made out of clay. It's actually possible to stretch the clay in a continuous manner so it ends up as a coffee mug, permitting that you don't cut or glue any clay you started with. Now look at the surface of a cube. Can we change it to a sphere by a similar deformation without cutting or gluing? Pretend that you now have a latex balloon cube rigid enough to stand even without air. If you blow air inside the balloon, the cube expands, and with enough air, you end up with a sphere. This special type of deformation, in which we're not allowed to cut or glue any part of the initial surface, is called homeomorphism. If two surfaces are linked by homeomorphism, then they're homeomorphic, and in the field of topology, they're regarded to be identical. A question that comes up is, how do we know which surfaces are homeomorphic to each other? Let me introduce the Euler Characteristic. For any given surface, the number of vertices minus the number of edges plus the number of polygonal faces is known as the Euler Characteristic, which is denoted by the Greek letter chi. For example, the Euler Characteristic of a cube is 2, since V is 8, E is 12, and F is 6. In fact, Euler proved that all convex polyhedra, surfaces like tetrahedra, cubes, and other prisms, have Euler Characteristic 2. Knowing this property, here is one of the first breakthroughs in topology. Two surfaces are homeomorphically equivalent if and only if they share the same Euler characteristic. Finding the Euler characteristic of polyhedra is relatively straightforward, but how do we do that for other surfaces? Well, it turns out that the Euler characteristic can be calculated for surfaces without even edges or vertices. Welcome to triangulation. Triangulating a surface is simply making a round surface spiky. To do this, we think of a round surface as a stretched out version of another surface with polygonal faces. On these polygons, we can then draw lines to divide them into triangles with the restriction that each side of the triangle is entirely shared by two adjacent triangles. Since the new surface is now comprised of various triangles, counting the vertices, edges, and faces is easy. Thus, the value v minus e plus f gives us the Euler characteristic of the original surface. If we wanted to determine the Euler characteristic for a torus, we can triangulate it by first thinking of it as a blown-up version of a punctured rectangular prism. Drawing lines to divide the faces of the prism into triangles, we can count the vertices, edges, and faces. This gives us an Euler characteristic of 0 for the torus. Great, but now here comes the real questions. Why do we care about homeomorphisms, and why is topology important? To answer the first, it turns out that if two surfaces are homeomorphic, then all topological properties are shared by them. An example of a topological property is simply connected, which means that any loop on the surface can be shrunk down to a single point. Knowing that all topological properties are shared is of great use to us. The classification theorem says that every surface is homeomorphic to either a sphere, a torus, a double torus, a triple torus, and so on. That means if we are faced with a difficult surface, we can simplify our task and study the properties of a surface we're familiar with, namely these surfaces. We can then extend this knowledge to our original surface, as the two surfaces must share the same topological properties. Now, for the second question, it turns out that topology has many applications in physics, biology, and other areas of math. Let's put it to the test. How do we know Earth is spherical without using any external information from space? We know Earth is a surface, but it could well be a torus. In fact, Eratosthenes' measurements and Magellan's circumnavigation are consistent with a torus-shaped Earth. Because Taurine spheres are not homeomorphic due to different Euler characteristics, they must have different topological properties as a result. In particular, Earth is obviously a simply connected surface because whatever loop you make, you can always adjust it so it becomes a point. However, look at this loop on a torus. No matter how small you try to make it, it cannot be shrunk down to a point. In fact, by the classification theorem, the only surfaces in 3D space that are simply connected are spheres, so Earth must be a sphere. Topology is fascinating, and we have homeomorphisms to thank for that. So the next time you're out with your topologist friends, help them out with their coffee and donuts, will you?